Okay, so here's what we were talking about last time. We spent a bunch of energy, bunch of time putting together this machinery that started with an algebra for linear transformations, which right away, a little weird, right? I mean, we think of linear transformations as functions. We don't think of them as objects with which we can do algebra, like multiplication. But nevertheless, we made some definitions and we created this algebra of linear transformations. We then created a specific framework within that algebra of linear transformations having to do with constant coefficient linear differential operators. Right? And we found that the algebra of constant coefficient linear differential operators is actually really, really good. Not only can you add, multiply by scalars, multiply by each other, you can also plug into polynomials, factor, right? Almost everything that you can do with regular algebra. It's commutative even. Right? So super observations. And the first thing that we did with that is we observed that L, being P of D, being that it factors just like P, the characteristic polynomial. I could rewrite the differential equation like this, and then I can move these factors around. All right, I made this slick move where I pushed this factor over here to the right, and then observed that if I can make this 0, certainly that would make this 0. So said differently, if I can solve this differential equation, I can solve that differential equation. And of course, solving this differential equation is easy. It's a natural growth equation. We already know the solution, right? So this is a really powerful observation that, whereas previously we literally built everything that we did in chapter 4 on the guess that maybe exponentials will work. And it turns out that they did, and that's fine and all, right? But we started off with a guess, and it's not very inspiring. Here we have a way to motivate why that was a good guess, right? Algebraically, I think this is super impressive. And let me say this a different way now. Because of this development, we have found a way to find this differential equation hidden inside of our original higher order differential equation. And that's really weird. Right? This is something we could not have done in chapter 4. You could make the case, I suppose, coming back to when we first started writing down this stuff, you could take the point of view that this alternative view of our differential equation is just algebra. This is just just a notational alternative. This is just a different way of writing the original differential equation, right? But that's just notation. Finding this differential equation inside of the original differential equation critically relies on this algebra that we set up. Could not have done this in chapter 4. Okay. All right, so that's what we were talking about last time. It turns out there's another couple of really great conclusions that we're going to be able to get with this algebra of linear transformations. So I'm going to start off with a quick observation. Oh, by the way, just to let you know where we're going, you may recall a long time ago, I asserted what happens to the solutions to the differential equation when you have a root with a multiplicity. Right? And we made this claim that, you take the exponential that you would have gotten from that root. That still works. But then start multiplying by powers of x until you get to, mysteriously, one less than the multiplicity, and all of those will also be solutions. I gave no demonstration at all that would work. I just asserted that it worked. And, we wrote it down a bunch of times. But I still have never proved that so far in this class. Okay, so I'm going to show you now how to prove that. And it's surprisingly straightforward. Okay, first a little lemma. It ends up being really convenient to have this algebra worked out. What does one of these factors, d minus r, right, the kinds of factors that show up when you factor these constant coefficient operators, what does d minus r do to functions like the ones that we're entertaining as possible solutions? Right? What happens if you get d minus r to one of these? Now, very importantly, notice that the r here in the d minus r and the r in the exponential, indicating what root this came from, are the same. Right? So this is just a, let's work out this algebra, see what it is for convenient use in a few minutes. So here's how that algebra plays out. D, take the derivative, product rule, and you get that. Right? R, keep in mind, that's the linear transformation that says just multiply by R. That gives you that. So d minus r on this function gives us this bunch of terms here, and then you notice that, oh, hey, look at that, those two terms cancel, and all you're left with is just this. So d minus r turns this function into that function. Now, what's particularly interesting about this is that something very simple happened. The form didn't really change very much, right? Monomial times e to the rx has turned into monomial times e to the rx. Right? So that's right off the bat, that's pretty simple. But even better than that, the exponent has reduced by 1, right? And then I get a constant factor out front of k. So, neat fact, the d minus r operates on these kind of candidate functions that we're interested in the following way. The exponent reduces by 1 and extra factor of k in front. Okay. All right. Now that's when k is positive. Note that if k is equal to 0, right, if there is no monomial, if it's just, e to the rx by itself, well, d minus r gives you just plain old 0 there. And again, that's just straight up calculation. Take the derivative of this thing, multiply minus r times this thing, add them up, they go to 0. Okay. All right. Okay, so with this observation, we're ready to do the proof now. Keep in mind what we're trying to prove. These differential equations, when you have a root with a multiplicity, you get a bunch of solutions that look kind of like that. To be more specific, if your characteristic polynomial has a root r of multiplicity m, right, then the assertion is that the solutions corresponding to that root, all of this form, notice the r, right, and the k, how many powers of x do you get? Well, all the powers of x less than m. Right, so this k here can be anything up through and including m minus 1. So this is just a rewrite of chapter 4 assertion that we made. Again, this is what we're trying to prove. And I'm going to prove this by explicit calculation, right? I'm going to take these solutions and I'm going to apply this operator L. I missed. I'm going to apply this operator L to those solutions. I'm just going to confirm directly that we get 0. So here we go. Now, keep in mind, k is less than m. So these m factors here, the m factors of d minus r, I'm going to break those up as follows. Now, k being less than m, I can certainly pull out k of those m factors. Because it was less than m and not equal to m, that means there will be at least one other factor here left over. And then, I don't know, there might not be any left over, but there might be some left over, maybe, maybe not, whatever. However many there might be left over, it's m minus k minus 1. Okay, so that's just separating some factors. And then now let's apply what we know about this algebra. Give myself a little space here. First, keep in mind, d minus r reduces the exponent by 1 and gives us an extra factor of k, and do that a bunch of times, and this is what happens. x to the k. First it turns into k times x to the k minus 1. And then you get a factor of k minus 1, and this becomes k minus 2, et cetera, et cetera. Apply that k, to keep going k times, and eventually all k of these factors of x disappear. And the scalars out front are k, k minus 1, k minus 2, etc. You end up with k factorial. So this is just a bunch of repeated applications of this observation up there. Not done yet, of course. Okay. All right. Next. D minus r on e to the rx gives us 0. Right, this k factorial is just a scalar. The scalar can just pop right out, right? D minus r, e to the rx, 0, as discussed above. And so it doesn't really matter what's going on with the rest of these polynomials over here. All of this differential operators, I don't really care how many derivatives you take. I don't care what scalars you multiply by. If you're doing all of that to 0, you get 0. Right? And so we're done. So these functions, these y's that we just tested, are solutions to that homogeneous differential equation, just like we asserted in chapter 4. Everybody see how that works? Notice again, it's specifically the algebra that makes this possible, right? I had to be able to take my P of D, my differential operator, I had to be able to factor it and move factors around in order for this observation to work. It was because and only because we had an algebra of these constant coefficient operators that any of this is possible. But with that machinery of this algebra of linear transformations, it's just a matter of noticing that it works. Okay. All right. So that ties up a loose end from chapter 4. Now, here's another loose end from chapter 4. You may recall we spent a bunch of time talking about how to find particular solutions, right? Undetermined coefficients. And in that undetermined coefficients chapter, we stated, and didn't come close to proving, but we stated a theorem about, look, here's what you should guess. Here's what the particular solution is going to end up being. There was a bunch to say in that 4.3 section. Let me just remind you, we had what I called at the time a naive guess. We spent several examples building up the plausibility of why this naive guess ought to work. You would think that this should work, given the structure of the right-hand side. Seems like a reasonable thing to try. Okay. We then also asserted, with no intuition whatsoever, that naive guess, in the case that r from the right-hand side is a root of your characteristic polynomial of multiplicity m, we just asserted that multiply by x to the m in that case. I gave you no justification at all other than, well, there was that sanity check of, well, at least it takes the terms that are obviously homogeneous solutions and therefore irrelevant to the particular solution. It slides them over by at least enough to where they're not obviously useless. That's not much, right? Okay. All right, so I'm going to show you here now. I'm not going to prove the business about the naive guess. I think that's plausible. We could prove it. We do have enough tools to prove this, that now that this works, but it's a time sink. It would take us half an hour, and it's just not worth the details and the effort. So I'm not going to prove that part. I think that's plausible enough. What I want to do is focus on why the x to the m. I want to give you a plausibility argument. I think a really good plausibility argument for why the x to the m. Okay, before we do that, let me confess. This theorem is not exactly the theorem that we wrote down in 4.3. You may recall that in section 4.3, the right-hand side over here that we were speculating about had sines and cosines in it. Right? This doesn't. There's no visible sines and cosines in how this is written down. So what gives? Well, you may also recall that in the theorem that we talked about in 4.3, the coefficients, the r in particular, were real. Notice here, r is now a complex number, right? So this this r right here, being a complex number, means that this e to the rx actually does have sines and cosines in it. They're just hidden as part of the imaginary exponential that's part of that factor. Okay, so then I'm going to make an assertion, and again, that we don't have time for the details, and you should not worry about the following details. But you remember we did do some examples where we realized that not only is e to the rx a linear combination of exponentials times trig functions, right? But furthermore, exponentials times trig functions are linear combinations of e to the rx and e to the r bar x, right? So that's just a matter of writing down linear algebra games and observing that works out. So I'm going to make the assertion here that these functions, being linear combinations of the functions from the 4.3 theorem, the 4.3 theorem functions being linear combinations of these functions, you can just play linear algebra games and show that this theorem I have circled in blue is equivalent to the theorem that's actually in 4.3. So this is an alternate version. You might call this the complex version of the theorem from 4.3. And it's more convenient to work with in this case, which is why I want to do it here. So if I can make you believe this theorem, then I hope you'd be willing to believe analogously to the theorem from 4.3. Okay, everybody good with that? Don't worry about the details. You're not responsible for the specific details of how this fact shows the equivalence of this theorem. Okay, so what about that x to the m? Where did the x to the m come from? Well, here we go. Keep in mind, we're considering the case where r is a root of multiplicity m. Well, that means this. R is a root of multiplicity m. But keep in mind, L is a characteristic polynomial on B. If that characteristic polynomial has a root of multiplicity m, that means that d minus r to the m is a factor. Right? Okay. I claim that this is the form to try. So we're going to stick that in there, right? The goal is that I could to show that I can make this work, to show that if I want to solve this differential equation with g being the right-hand side that's given, that this blue form here will work given that L is this green form here. Okay. So, here's where this goes. We go back to the page before. And remember, we have this rule that we figured out as to what d minus r does. D minus r, whenever you have a power of x times an exponential, with the r's matching up, d minus r is going to take that exponent and reduce it by 1. And then, yeah, there's going to be a constant out front. The constants out front end up not being particularly important here. Okay, so the power of x reduces by 1. Let me say that a different way. This d minus r effectively kills, erases, however you want to say it. It gets rid of one of the factors of x. D minus r gets rid of a factor of x. Way to think about that. So that's what we're going to see happening here. So now looking at our setup again, let's focus our attention on this right here. Keep in mind, each d minus r is going to get rid of a factor of x. Well, I've got m of these d minus r's. So if I put m x's right next to them, what are these d minus r's going to do? Well, they're just going to get rid of these m factors of x that I stuck right here. Right? So those are going to go away. Now, yeah, it's going to change you get an extra factor of k, and so, as many of these factors, every time you get rid of one of these x's, yes, the scalars out front change. So these c's are going to turn into other constants, d, whatever. I don't details as to what the relationship between the c's and the d's are, but that's predictable stuff that you can just write down. That's details. The point is, the d minus r's kill the x's, and thus giving you, instead then of this differential equation to solve, we now have this differential equation to solve. Notice that the polynomial r is not a root, right? All of the factors of d minus r we already pulled out. So r is not a root of this, and we've already argued plausibly that things that look like that will solve these differential equations. So the idea is you can use the naive guess to solve this differential equation down here. Once you know what the d's are, you can back solve and solve for the c's. So that's the big idea. This x to the m, these x to the m's are what allow you effectively to get rid of the awkward d minus r factors, thus leaving you with the naive case. Okay, so anyway, it's just a plausibility argument. I think it's a reasonably good plausibility argument, and I just wanted y'all to see that. Does anybody have any questions about that so far? Yes? Okay. You can talk to me after class if you want. Feel free. Yeah. Anybody else? Feel free. Okay. All right. Okay. So, it's a long way to go. I'll grant you, right? We have to set up the algebra. We have to make the definitions, show that algebra works, set up the specific machinery for this specific application. But as a result of that, we get some neat conclusions. We get a motivation for where our solutions came from. We get a proof of the theorem about what to do with repeated roots for homogeneous equations. And we get a lot of plausibility, at least an explanation, of where these factors of x to the m come from in the particular solution. Okay. All right. So that's it for 5.2. On to 5.3. By the way, let me go ahead and make the announcement now. 5.3 is a really long section. There is absolutely no chance we're going to finish it today, seeing as we have 27 minutes left. So today, being the cutoff day for the exam, don't forget we have an exam next week, right? Wednesday, right? On Halloween even. How scary. Right? So today, being Friday, is the cutoff day for the material, right? So 5.2, section 5.2 will be the last material that is fair game for the midterm on Wednesday. I'm going to send out an email on as soon as class is over, sometime soon after class is over, with other details. But morally, it's going to be pretty much everything from where we cut off last time up through and including 5.2. Okay. All right, so 5.3, a big section. It's going to take us at least 2, probably more like 3 days to cover all the material in this section. It's just a lot of stuff. Start with a quick observation. We already know this. Right, this was we talked about this in section 5.1, and I left this as an exercise for you guys, and I hope you all have taken a moment to do this. What I asked you to show was that if you think of a matrix as a function, just show that function is a linear transformation from Rn to Rm. Right? Okay, so all you got to do to prove this result is put a linear combination in and confirm with the algebra of matrices that you already know, confirm that as you would hope from linearity, you do indeed get the appropriate linear combination out. Okay. Good exercise. Y'all have already hopefully done that. So here's what I'm going to show you now. And that is, this arrow actually goes the other way also. This is very far from obvious. Not only is it true that all matrices are linear transformations from Rn to Rm, but furthermore, every linear transformation from Rn to Rm can be thought of as a matrix. How would we go about proving that, right? Just because it's linear, how do I know that there's a matrix that represents it? Okay, it is a remarkably convenient proof. We've got a linear transformation. T is known to be a linear transformation. I'm going to show that there is a matrix that represents it by producing the matrix. And here is the matrix. The matrix is defined by its columns, one at a time. The columns, each column is the image of the corresponding standard basis vector. I claim that this works. You take your linear transformation, see what the linear transformation does to all the standard basis vectors, make those outputs the columns. This is the matrix that represents that transformation. So it's easy to confirm that this works. It's just a straight up calculation. I want to confirm, keep in mind, my goal is to confirm that this matrix, I need to show that matrix indeed represents the linear transformation that we started with. So I need to show that T of x is equal to AX. And I'm going to do that with this calculation here. Notice you can sort of cheat and get down to the result. See, it's going to work. AX is T of x as follows. That's how matrix multiplication works. Right? A matrix with columns like that, you multiply by taking the appropriate linear combination, the appropriate being from the coefficients of the vector, linear combination of the columns of the matrix. That's from chapter 1. So that's the first step. Don't forget by our construction, let me go back to green here. By our construction, the columns are the images of the basis vectors. Right, that was our choice. This is just an observation that T is linear. Right? Linear combination of outputs, linear combination of the corresponding inputs. Right? This is straight up linearity. And then you just have to make the convenient observation that this vector here is exactly x. Right? That's just the observation that the vector whose coordinates are x1 through xn is x1 times e1 plus x2 times e2, etc. So y'all may remember this fact from, again, way back in chapter 1. This is one of the nice things about the standard basis vectors. Standard basis vectors have the feature that when you take a linear combination of them, the coefficients in the linear combination are the coordinates of the resulting vector. How about that? Okay, and so proof done. Right, as required, this matrix set up in that way represents the linear transformation. Let me take a pause here for questions. Does anybody have any questions? Yep. Mm-hmm.
There was a problem on the homework where you were given some functions and their images, or some vectors and their images.
Okay.
And this sort of thing seems to work out. Is the only requirement that those columns are a basis?
I don't know the specific question that you're asking about, so I'm not 100% sure how to answer. But with linear algebra, there's lots of situations where the way the algebra works out is kind of similar because ultimately, well, in fact, everything's linear. And so it's not too surprising that the algebra tends to work out in similar ways.
So if you have A1 through N that form a basis that aren't the standard basis vectors.
Yeah, well, so then this algebra won't 100% work out because because we need these to be standard basis vectors in order for this to work out. It's got to be the standard basis for this exact result to work. But there are
a matrix.
Yeah, there's a way there's a kind of a version of this for other vectors, for other non-standard bases, but it's not exactly this.
Okay.
Yeah.
So then you can actually write the function if you're given enough.
Yeah, that's right. If you have any basis, then you have enough information to at least compute the function, but to represent it with exactly this matrix, it's got to be the standard basis.
Okay.
Yep. Okay. Neat thing then. You can think of matrices and linear transformations from Rn to Rm as being kind of the same thing. You give me a matrix, I know it's a linear transformation. You give me a linear transformation, I can represent it with a matrix. It's like they're the same thing. Again, in this context, Euclidean context, Rn to Rm. Alrighty, let me show you an example of how to capitalize on this. Neat fact here. I'm going to have to sit for this, draw the picture. I want to talk about rotations in R2 around the origin. Y'all may have seen the following result in Math 212. Those of you who took Math 212 with me have definitely seen this. But anyway, here's a neat observation. Rotations in R2 are linear transformations. Doesn't feel like they'd be. Rotations involve turning. Turning feels like there's something intrinsically curving about the process. But the resulting function of input vector to output vector is a linear transformation. And here's the justification I'm going to give you. If you have an axis system, and suppose you have a couple of input vectors, maybe, I'll do this in blue, maybe let's say that vector and that vector. And you take some linear combination of those vectors. As indicated by that parallelogram, right? What would happen if you just rotate the entire parallelogram? Let's just look at what you get when you let's rotate the whole thing. Let's see here. I'm going to not going to rotate it very much to make my picture not too complicated, but something like that. And let's see, I got to rotate the whole parallelogram as well. So I've rotated the whole blue parallelogram to give me the green parallelogram. And now I make the following observation. What this, and let me zoom for convenience. Let's look in here. What this says is if I have a couple of vectors, right? If I add and then, take a linear combination, combine in some way. If I combine and then rotate, well, of course, I get to the vertex of that parallelogram, right? What if I do it in the other order? What if, instead of combining and then rotating, what if I rotate first and then combine? Well, I get again to the head, to the vertex there of that parallelogram, right? So, said differently, the fact that parallelograms, when you rotate them rigidly, remain parallelograms, right? Because of that, it doesn't matter if you combine and then rotate or rotate and then combine. In other words, rotations commute with linear combinations, and therefore rotations are linear transformations. And that ends up being a tremendously powerful fact, the fact that these are linear transformations. So let's capitalize on that now. We have, in fact, we have a linear transformation in R2. We have a linear transformation from R2 to R2. And this theorem says if you have a linear transformation from R2 to R2, you can represent it as a matrix. Right? And furthermore, not only do I know I can represent it as a matrix, but I have a formula for this matrix. The matrix that represents my linear transformation has columns that are images of the standard basis vectors. And that's all there is to that, except for some details. So I can understand the rotation process by simply computing the rotation of the first standard basis vector. That becomes my first column. Then a rotation of the second standard basis vector. I'll show you the pictures of those in a second. That becomes my second column. And there you go. There's your matrix. That matrix does rotations by whatever the angle theta is. Okay, yeah, question. Yeah.
So, I'm assuming since you majored in physics, you studied stress and strain, right?
Actually, no. So that's more, I sort of always viewed that as engineers' problem. That's not our problem. Yeah. Sorry. So I don't know anything about that. But if there's a related question, I mean, you can show it to me after class. I'll be happy to look at it. But I don't actually know anything about it.
Yeah, it's not really a question, but I thought.
Oh, okay.
Because I can relate it to one of our other classes that some of us are taking right now, which is EGR 201.
Yeah.
And so we're given stresses on a body.
Okay.
And that body, if it's rotated, the stresses will change, but I think it's a linear transformation.
Oh, okay.
So I thought it was interesting.
Oh, okay, yeah, it could well be. If you want to show me the documentation you have on it at some point, I'll be happy to look at it and see. But yeah, it very well might be. Yeah. Okay, so let's do a couple of the details here. Now this is I'm going to be real quick about this, but rotating standard basis vectors is actually pretty easy. So here's our first standard basis vector E1. Right, that distance is 1. It points along the x-axis. If I want to rotate that. Right? How do I rotate E1? Well, there we go. That distance is still 1. This angle now is theta. And it's just not hard to find the coordinates of that point. Cosine theta, sine theta, right? Basic trig. And there's our first column. And then likewise for E2. So a little bit of geometry details for E2. I'll let y'all work out that one. The punchline, though, is that will be that second column. So, okay, anyway, neat application. Notice what's weird about this is theta can be any angle, and we have now a formula for how to rotate any vector that only works capitalizing on the fact that being a linear transformation, I really only had to understand it on standard basis vectors. So the linearity, the fact that it's a linear transformation, was essential in this analysis. Okay. All right. All right. So a quick comment before we go on to the next thing. Please be sure to memorize this formula right here. That if you want to represent a linear transformation with a matrix, then the columns are the images of the standard basis vectors. I like to think of that as a little phrase that you can repeat to yourself over and over again until you've unavoidably memorized it. The columns are the images of the standard basis vectors. Just make sure that you're really, really solid on this. This is a very, very important fact in linear algebra and relating matrices and linear transformations. Okay. All right. Now, we have oh, yeah, question.
Can you explain or provide for the second standard basis vector why it's negative sign?
It's in the geometry of what happens when you rotate the second standard basis vector. When you rotate that around, you end up with a minus sign there. Talk to me after class. I'll be happy to show you. Yeah. It's a geometric thing. Yeah. Okay, so we've got ourselves inadvertently into a weird situation. Oh yeah. Okay.
Going back to the other page.
Okay.
Does AI have to be different than AN, for example?
Oh no, they don't have to at all. I mean, sometimes a linear transformation like these two vectors might coincidentally be the same vector. Perfectly fine. What you do always, though, whatever that linear transformation is, just see what it does to the standard basis vectors, and whatever those end up being, make those the columns. And if some of them are the same, so be it. If they're all different, okay. Yeah, totally. All right. So here's the awkward situation we're in. We have a product on linear transformations. We talked about that last time. That's from the algebra of linear transformations. You multiply linear transformations by composing. Okay. All right, fine, no problem. We can define anything we want to. We also have a product on matrices, and we defined that a long time ago, right? And many of y'all, of course, saw the definition of matrix multiplication even longer ago, perhaps as long ago as high school. Okay, fine. There are different contexts. You can make different definitions. I mean, the definition we have for matrix multiplication, unrecognizable from the definition that we've made for multiplication on linear transformations. Not a problem. They're different things. Up to now, we haven't seen any connection between them. Here's our problem, though. We now have this very strong connection. We now have this point of view that linear transformations and matrices are really kind of the same thing, at least if you're talking about from Rn to Rm. So now, instead of having two completely different products on completely different objects, so who cares? Now we have two completely different products on ultimately the same things. And this is scary, right? So we have to worry, do we now have actually two different kinds of multiplication? In other words, if I multiply two linear transformations in the linear transformation sense, if I were to think of those linear transformations as matrices, would the matrices multiply in the matrix sense to give me the same result, or are they different? So, problem. Something to worry about. For a few moments until we do this calculation to see that they're exactly the same thing. So it's not actually a bad thing. It's just I want to point out that it's something that has to get checked. So if you have a linear transformation T, if you have a linear transformation S, each thought of as, shorthanded by a matrix. So T represented by A, S represented by B. Suppose you multiply in the composition sense, right? That's going to be represented by some matrix C. Is C, fingers crossed, is C equal to A times B? That's our big question. Yeah, it is. So it's fine. It's nothing to worry about, like I say. But here's how you know this matrix, right? Keep in mind the columns of a matrix, right, are the images of the standard basis vectors. We just got through talking about that. So this matrix, whatever it is, its columns are the images. Keep in mind it represents ST, the images of the standard basis vectors. Multiplication of transformations is composition. T is done by multiplication by A. S is done by multiplication by B. There's a temptation to play associativity games and just kind of move parentheses around like that. Let's not do that yet. I'll reveal why momentarily. Let me instead just observe this, that when you multiply a matrix A times a standard basis vector, keep in mind the images of the standard basis vectors are the columns. Right? Columns are the images of the standard basis vectors. And so notice now this is the ith column of BA. So as we would have hoped, the ith column of C is the ith column of BA, and therefore C is equal to B times A, just like we wanted. Okay, so multiplication in the sense of linear transformations is equivalent. It's just different notation for the same thing to multiplication by matrices. Okay, yes?
So it's composition until like the third time that it goes to multiplication?
Where are we?
S, when it says C of I equals ST.
Yep. So this is a multiplication of linear transformations. This is composition of linear transformations, but that's what multiplication is, right? And then here, I've got a vector that I'm multiplying by a matrix, and the resulting vector there, I'm multiplying by that matrix.
Is that still composition? Is that a different
This is matrix vector multiplication, and this is matrix vector multiplication. Yeah. Okay, so really, really good news. When you multiply linear transformations in that sense, it's exactly the same as multiplying matrices in the matrix sense. So, don't have to worry about having distinct multiplications. Now, why is this useful? Why is this important? This is actually really, really valuable. And you may recall way, way back, section 1.2, the very, very start of the term, I never proved this. Right? We're closing up loose ends here at this point. So I proved a bunch of facts about matrix multiplication, but I never proved that matrix multiplication was associative. The book has a proof of this in chapter 1, and it involves sigma notation and moving indices around, and it's very notation heavy and opaque and unsatisfying and bulletproof. Yeah, watertight, absolutely, right? But it's just notation, and then it worked, I guess. I've never really found that satisfying. I never liked it. So the reason I don't like to go through that proof that the book does is because there's a much more satisfying proof that we can do now that we have these tools. Here's the idea. We just got through showing that matrix multiplication is the same thing as multiplication of linear transformations. So if I want to know why is this true, well, I could instead ask, why is this true? It's the same question, right? And the associativity of linear transformations is really easy to prove. It's, I'm going to say, borderline obvious. The algebra goes as follows. If you want to show these two functions are the same function, well, by definition, what I need to show is that R st of x, I need to show that is equal to rs t of x. This is what I want to know. But good news, both of these, straight out of the definition of how how linear transformations multiply, both of these are R of S of t of x. And so that, right? I mean, think about this product of linear transformations says first compose S and T, and having done that, then compose with R like this, thus giving you R of S of T of x. Right? Over here, we're composing the R and the S, and then subsequently composing the T. So I have R of S of T of x. The only difference is where's the dramatic pause. Right? But they're the same thing. In both of these cases, we're taking x. First, we're plugging into T. Then we're plugging into S. Then we're plugging in the R. Doesn't matter where the parentheses are. So it's immediate that linear transformations multiplication is associative. Therefore, immediately, matrix multiplication is associative. So I find this much more satisfying. Right? Think of matrices as representing linear transformations. Composing functions, of course, is associative. Much more satisfying than a bunch of notational arguments such as they have in chapter 1. All right, let's see here. I have 60 seconds. Let me use those 60 seconds for this one last point here. This is a cultural point, but I think it's good for everybody to know. So in this book, we start with matrices and systems of equations and things that we can kind of relate to and that we can get our hands on that help us answer questions, things that are more satisfying. And then from that, we eventually define some abstractions. We define, vector spaces and linear transformations. Okay. Many linear algebra books do it in the other order. In fact, from a mathematical point of view, it really makes a lot of sense to do it in the other order. So, lots of linear algebra books. This is chapter 1, section 1. What is a vector space? chapter 1, section 2. What is a linear transformation? Right? They write that down first. Right? And then, having written all that down, you have a great way to motivate, what's a matrix? A matrix is just a shorthand representing a linear transformation, just like we've done recently. What does it mean to add two matrices? Well, just add the linear transformations. What does it mean to multiply the two matrices? Where does this mysterious, weird definition of matrix multiplication come from? It's just composed of linear transformations. Very natural, right? So this gives a natural motivation for all the stuff that we just kind of, at the time in chapter 1, we just wrote down some definitions and said, oh, this is going to work conveniently for us. Trust me. Right? So be aware that there is this alternative point of view, and we just chose to do it one way in this class. See y'all later. Have a great weekend.